Good morning, everyone. Thank you for joining us on this virtual astronomy day. Usually we're set up at the chapters at Blair, but global circumstances dictate that we're all doing this online now. So the presentation will be about solar astronomy in general, how to safely observe the sun, and just some cool features about the sun. So starting with it, and just gonna click here. First step is always safety. So usually I'm presenting to younger demographic children. However, the safety applies to adults as well. So what we here have is the solar radiation spectrum. So it's divided out into three parts. We have the visible part, which is the part that our eyes can see. Then we have the upper portion, which is the infrared, and the UV light as well. More than half of the energy coming off the sun is in the infrared part. So if you're looking directly at the sun, you will end up quite literally cooking your eyes. So what I always tell the children is, when should you look at the sun? And the answer is absolutely never, unless you have special equipment that I'll talk about shortly, or in one very specific scenario, which I'll cover later on. So keep your ears perked for that. So what actually is the sun? Because we haven't actually covered that yet. So the sun is actually just an average star in our galaxy. It's actually not that big, not that small. There are many stars that are orders of magnitude larger than our star. And it's about 94% hydrogen, 5% helium, and then traces of other elements. Now, a big ball of hydrogen, it's not very specific. So how big of a ball of hydrogen? About that big. So this right here, I hope you can see my mouse. This is the Earth about to scale, and this is the sun to scale. So just imagine anywhere where you've ever traveled, and for our generation, probably anywhere where you will ever travel, is confined to this one little dot, and this is our average sun to scale. So you could fit actually 110 Earths across the diameter of this sun. And if we're talking about volume, we could fit about 1.3 million Earths inside of the sun. So what is the sun still? It contains 99.8% of all the mass in the solar system. So you are probably familiar with the other planets, Jupiter, Saturn, Neptune, and some of the smaller ones, Mercury and Venus. All the comets, all the asteroids, anything in the solar system accounts for 0.2% of the mass. The sun comprises 99.8% of the mass. It's responsible for all of the life that we know of in the solar system. So if you look at the Earth, any food chain, any energy production can be traced back to the energy that is being produced on the sun right now. And how far is away the sun? 8 light minutes. So what does 8 light minutes mean? Light travels very fast, 300,000 kilometers per second. If the sun were to stop shining right now, we would actually receive sunlight for another 8 minutes until the lights would go off. So 8 light minutes away is how far the sun is. Jim spoke about this earlier, but one of the features of the sun, or one of the areas of the sun, is what we call the photosphere. So this is the furthest inside of the sun that we can see until we can no longer see into the sun. And it's a layer on the sun that's about 500 kilometers thick, and is considered sort of the outer shell of the sun. However, the sun is entirely gas. You would not be able to, quote unquote, stand on the sun if we could get there. It is just the innermost region of the sun that we can see directly. Each one of these dark spots on the sun is a sunspot, as Jim mentioned. So it is a region of the sun that is slightly cooler, and it is an active region on the sun which could lead either to prominences or solar flares. Again, keep in mind how big that Earth was in relative size to the sun. So each one of these sunspots, which is just a giant region on the sun, is 2 to 3 times the size of the Earth. The other layer that we were talking about, and this was the hydrogen region that Jim was showing, is called the chromosphere. and that's about 2,000 kilometers thick. And here we can see some excessively large solar prominences out on the limb. All these past 3 shots were taken by advanced NASA telescopes in space, so that is why they are so much more elaborate than what we can show directly with our telescopes. So how do we actually observe the sun? So we have something called white light observing. So that's the visual band at safe intensity levels with no IR. If you remember this from your physics class or similar, we don't actually have white light. There's no such thing as white light. It is just what our eyes detect as white light when we receive all the colors of the spectrum into our eye. So you can use your existing scope or several other options, and it's actually the most economical way to observe the sun. Now, we receive this question as astronomers very often. Did you have to mortgage your house to actually start this hobby? And the answer is only if you want to. So the cheapest way to observe the sun, the cheapest way to observe the sun is solar glasses. So these are glasses that are made of cardboard for the frame, and then a polymer and mylar film covers the eyes, and that is enough to reject the sun to safe levels so that you can view the sun. If you buy them in bulk, you can get them down to 35 cents a piece, and this is perhaps the second cheapest way to do astronomy, with the cheapest way being just going out tonight and looking at the dark sky, and then you are doing astronomy. So what can you see in white light observing? These are all pictures from Jim. So the filters here that were used were red and green, and sometimes that's just a trick that we use to increase the contrast in the picture so that we can see more detail. However, without any colorization filters, the view would be this black and white image here with the sunspots that Jim was showing just recently. Another method by which we can observe the sun is with a telescope, however, without any filtration. So this is a normal refracting telescope without any filters, and you place a screen at the focal plane behind the telescope, and you can project an image of the sun onto the screen. You can see sunspots, but the picture is not as detailed as it could be due to insufficient filtering in the train and resolution. This is the second cheapest solution after the solar sunglasses, of course. We have these types of filters, solar filters, that we can place directly on our telescopes. So this left one right here is a glass filter, while this right one here is a thin film similar to the one found in the solar sunglasses. So you attach this directly to the front of your telescope or the objective of the telescope, and this filters and rejects all of the sunlight and allows you to use your telescope. This is a Herschel Wedge. So this is a piece of equipment that plugs into an existing refracting telescope. On this diagonal right here, you have a partially reflective mirror, which reflects about 4.6% of the sun's intensity up into the eyepiece, where you can further filter or view it. And on the back of this device here is usually a piece of ceramic or some piece of mass that can absorb all the energy that is passing through the telescope. So again, a mirror here bounces part of the sunlight back up into the eyepiece, and then the energy gets dumped into this hot piece of ceramic back here. This gives us the best views in white light observing and is what we try and use as much as we can. So we have our calcium observing, which Jim was also showing, which is very narrow band and near UV, so about 400 nanometers. Now, what do I mean by narrow band? We spoke about the spectrum of the sun earlier on, where we have blue or violet light at one end of the spectrum and then red all the way at the other side. In between there, there's lots of other colors of the spectrum. When we're doing narrow band observing, we're looking at just one tiny sliver of that light. And in this specific scenario, it's just these 5 nanometers of the spectrum that we want to look at. You can use your existing scope and add some energy rejection filters, which I'll show shortly, that let us view that. This is a slightly more expensive way to observe the sun. And I have here camera usually, visual possible for some, and I'll explain that just after I show the pictures. So these are the views that you could get through the telescope after you have actually imaged the picture. So you saw Jim's image, which was a live view. However, these are images where we take thousands of photos in a short succession, and then we use a computer to stack them on top of each other and sharpen the image. So these are all pictures that we have taken with a calcium K telescope. Now I said it was usually reserved for photographing. However, there's an interesting biological explanation here. So as humans age, our cornea actually becomes more opaque to certain wavelengths. And this wavelength is near ultraviolet. So as humans get older, you actually become less sensitive to this type of light. So I've had this type of telescope set up once in the past, and I'm happily looking through the eyepiece and looking at a purple disk of the sun. However, someone who's a bit older will come to the scope and say, hey, your scope is broken. And it turns out some humans simply not see this wavelength of light, while some can. So an interesting tidbit there. I did want to cover very briefly just the technology that is used. So I'm going to be mentioning the word etalon a couple of times. And etalon is a fancy name for 2 mirrors that are placed parallel to each other like so. And as the light from the sun comes in, the light bounces back and forth due to some physics properties and destructive interference. All the light that we do not want to look at gets filtered out and rejected, while all the light that we want to look at makes it through this parallel plate of mirrors. So this is actually what makes a solar telescope possible and is found in all solar telescopes except for the Whitelight one that I covered. So that is an etalon. When I say bandpass, this is a pictorial representation of what I mean by bandpass. So we have the UV light here at 400 nanometers, and then the red light all the way up here at the 600s. And when we say bandpass, we're looking at just one wavelength of the spectrum and rejecting absolutely everything else. So if we want to look at something called Hydrogenalpha, which I'll cover shortly, we're just looking here at around 655 nanometers and rejecting all other light.
Bojan, we have a question from Alaura online.
Yep.
Saying, can we get some of the things to block the sun for any type of telescope?
Can we get some of the, could you read that again?
Can we get some of the things to block the sun for any type of telescope?
Yes, so going back, I can, oops. If you have any telescope, really, you can buy one of these glass filters or mylar film filters, which are quite affordable, maybe $100, $150. And you can plug that into any telescope and do white light observing. That will let you see the sunspots, and you don't need more than about 6 inches of aperture. If you have a scope that's bigger than 6 to 8 inches, you would actually want to just cover a piece of the sun because you don't need all of that light gathering power. If I understand your question, you could use these white light wedges on any refracting telescope. And then these calcium K, which is where we're at anyway, these systems generally also need a refractor type telescope, and this etalon system can be plugged into most refracting telescopes with some additional filters. This is where we start talking about perhaps the price of a smartphone for a component that you want to plug into an existing telescope. And it's about for $800 to $2,000 to look at the calcium portion of the sun. These are additional Etalon, more complex systems with a price tag to match, which actually use heating of the two parallel mirrors or Etalon to change how we actually tune the system. They provide sharper and higher contrast views, but are also more expensive. So this was the final view that Jim showed just previously, which is called Hydrogenalpha, and that is looking at what hydrogen does on the sun. So that was looking at the chromosphere at this wavelength here, about 656 nanometers, and we're doing very narrow bandpass. So remember, just a tiny sliver of the sun spectrum is making it through the telescope, and that's what we're looking at. These options all require a tunable Etalon, and I won't go into great detail about that, but in short, the sun is rotating. The prominences on the sun are moving either directly at us or slightly off center from us or to the left. On top of that, the Earth is moving, and through that process, we actually get something called Doppler shifting. So we would like to look at this wavelength. However, because the Earth and all the objects that we're trying to look at are moving at almost relativistic speeds, we actually need to tune our Etalons to actually not look directly at 656 nanometers, but slightly to the left or slightly to the right in the spectrum, depending on the relative movement of the objects. This is the most expensive way to observe the sun, and also the most awesome and exciting way to look at the sun. So these are also all taken by Jim. The views that you would get through an eyepiece would be these three pictures right here in red and orange. Sometimes we falsely color the image with a different color in order to improve the contrast so that we can see more details. As we described, there's sunspots right here, there's prominences on the outer edge, and then the filaments, which are these, what I call scars on the sun, which are really just the same prominences, just facing directly at us. Fun tidbit, when some of these prominences actually separate, they can travel through space, they can hit the Earth's magnetosphere, and then we get northern lights, which you can see actually in my background. So even when we're looking at the northern lights, we are actually looking at pieces of the sun that made it through space and interacted with the Earth's atmosphere. And we're back to our Etalon systems for hydrogen observing. So these are Etalons that can be attached to existing telescopes, and they allow us to look at just what hydrogen is doing on the sun. These can be used with existing refractors, and the price can start getting up there. Most of us actually, however, also have dedicated Hydrogenalpha scopes. So this is sort of the Ferraris of the telescope world, if you'd like. But these telescopes have been designed from the ground up to just look at the sun and just look at that one spectrum of light on the sun in Hydrogenalpha. So we have a certain telescope for just one wavelength on the sun, and you will be seeing a view through this Coronado telescope actually shortly, I believe. These have the same Etalon systems available to them, where we use heat to actually change how the Etalon is tuned, and they provide pleasing views, however, with a price to match as well. I didn't think I would get the word corona into this presentation. However, here it is. So we have corona observing of the sun. So what we have here on the left is a drawing actually of the sun's corona. Now, usually the sun's corona is too faint to see directly because the sun is so bright and it would overpower the view of the corona. However, in one very specific scenario, and I mentioned this earlier, there's only one scenario where you can look directly at the sun, and that is right here. So if you notice here, we're seeing prominences on the sun on the edge. However, we're not looking at the surface of the sun here, we're actually looking at the moon. And what happens is in a total solar eclipse, the moon sits directly between the sun and the Earth, and blocks out the disk of the sun perfectly, allowing us to see prominences on the limb as well as the corona. Now, lucky for us, April 8th, 2024 is an exciting day. We have a map here of our Ottawa region. We have Ottawa, Toronto, and Montreal. And on this day, the sun will be passing just to the south of us through the Great Lakes and then the Adirondacks and northern New York. And there will be a total solar eclipse. So the moon will sit between the sun and the earth and will perfectly block it out. And I mentioned earlier that there's one scenario under which you can look directly at the sun. This is it. And the last solar eclipse that I saw was in 2017 in Atlanta. And it is a absolutely fascinating experience. You could see stars in the middle of the day because the sun is blocked out. Birds start chirping because they are confused. They think it's almost nighttime, even though it can be in the middle of the day, and is a incredibly powerful and moving experience. So what I recommend you do is start planning for this date 4 years in advance. Buy some solar sunglasses because people start hoarding them shortly before the solar eclipse, and make sure you are equipped and jump in your car and make sure to view this total solar eclipse somewhere on this line when the time comes. You will not regret it.
So Bojan, if I can interject with a comment there, one additional thing to do is to check the weather, because there's a less than ideal chance of us having clear skies then.
That is true. If we have a line here of totality, so if you're willing to travel down to perhaps Texas or Mexico for some nicer weather, that is an option as well. And the last thing I briefly wanted to cover is what to make of all of this. So solar astronomy, it's fun, it's interesting.
Bojan, before you do that, let me just
Yes.
interject with a question on this slide. Is there, from Tom, is there any value being as close to the central line as possible? Or do you have to have the same, could you have the same experience anywhere between the northern and southern limits?
Good question, Tom. You would absolutely want to be as close to the center line as possible. The closer to the center line that you are, the longer the perceived solar eclipse is for you. So the one that I saw in Atlanta was about 2.5 minutes long of totality. The further you move away from that line, the more seconds you shave off of totality.
And Bojan, just a warning that you've only got a few minutes to go, and I have one question to interject when it's convenient.
Awesome. So briefly, just the last piece I wanted to cover. Solar astronomy is fun. However, all of us astronomers here have looked through a telescope many times. So that's why we do outreach events like this, to get everyone excited about science and technology. So briefly, just wanted to cover the Charley Bates Solar Astronomy Project, which is a global world's largest, highest volume hands-on astronomy outreach program. We go to schools all around the world and just get kids excited about science and technology and learning using solar telescopes. So we've had over 2,200 events in 27 countries, and almost 750,000 adults or children have received sunglasses or looked at the sun through these telescopes. So it's a great way to get our next generation of scientists or doctors or just members of society educated about the wonders of space. I have 3 more minutes for any questions.
Okay, I'll interject with a question from Peter. Are there other solar elements that have specific emission wavelengths we can use to view the sun to see other perspectives?
That's a good question. I'm sure there is. Off the top of my head, I don't know them, but there are other elements that are present in the sun that we would be observing at the amateur level. I have not seen any of that. One other piece of equipment that I didn't mention is spectroscopy. So what you do is you collect the light from the sun, and you can see all the emission and absorption lines of the sun. So hydrogen does not only have a hydrogen alpha band, but a beta, gamma, delta, epsilon band. All of those are different emissions at different wavelengths. So short answer is absolutely, not at the amateur level though.